Today we're going to start Chapter 2, Plate Tectonics and the Structure of Ocean Basins. Well, Earth is a unique planet because it has large amounts of liquid water, the oceans, on its surface. Because of that ocean, our Earth is just the right distance from the sun, not because of the ocean, but because it's just the right distance from the sun, the oceans don't dry up, they don't freeze over, and they keep our planet at just the right temperature. Covering 71% of the Earth's surface, they regulate the climate and the atmosphere. Now, the structure of the Earth. The Big Bang Theory says that the Earth was thought to have originated 4.5 billion years ago. God said it, and bang, there it was. Due to heat associated with these events, the early Earth was most likely molten, and then over time, as it cooled down, material settled by density as the materials cooled, with the denser materials like iron moving to the center of the Earth. Heavier material settled deep in the Earth, and lighter components formed the thin crust. And then the Earth's oceans and atmosphere began to form. Again, the location of the Earth relative to the Sun at 93 million miles is perfect to allow water to stay liquid and not freeze and not evaporate, which is essential for sustaining life. Let's look at the structure of the Earth from the inside out. Now, in the very middle of the Earth, we have what we call the core. And the core is divided into the innermost and the outermost core. The innermost layer, called the inner core, is about 1,200 kilometers wide, and it is liquid iron nickel. And the outer core, which is a little bit wider, 2,300 kilometers, is liquid iron nickel. Now, how do we know if it's liquid and solid? Well, that's a great question, because what happens is when earthquakes occur, they transmit waves through the planet. These waves are known as seismic waves, and we detect those and analyze them, and we've discovered that the waves will change as they pass through certain parts of the planet. And scientists believe that the shift in the seismic waves is showing the difference between how they travel through liquid and solid. So we're basing this information presented today on that seismic wave data. Now, once you move out from the outer core, you get to the lower mantle. The mantle is actually the thickest part of the Earth's layers, the thickest layer at 2,300 kilometers, plus, well, in this picture it's about 2,800 because you're adding on the upper mantle. So the mantle is the thickest part, and it's composed of a more variety of materials, minerals, other than just iron and nickel. Now, what is it? Is it solid or liquid? That's a great question, too, because the mantle is so hot. They're all hot, but it's really hot, and so it's like a solid, but it moves slowly like a liquid. So it's what we call in science a semi-plastic composition. And then, of course, on the outer part of the Earth is the crust where we all live, and this is the thinnest portion of the Earth, like the peel on an apple. Now, when we talk about how hot they are, let's go back to the inner core. The inner core is actually the hottest layer. And you usually would think of something being hot and being a liquid, but because there's so much pressure pushing on the inner core from the outer core and the mantle and the crust, so much pressure on those molecules of iron that they can't move, so they become solid even though they're so hot. The outer core doesn't have quite as much pressure, so that's where the iron nickel is liquid. And then you have the mantle, which is, like I said, a different composition of materials. It's a very, 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 very thick liquid, solid-like material. And then, of course, the outer crust temperature is the temperature of the air around it, basically. Now, there's two types of crust on the Earth. There's oceanic crust and there's continental crust. So oceanic crust is exactly where you would think. It's under the oceans. And it is different from continental crust in several ways. It's made up of a darker colored mineral called basalt. It's denser than continental crust, so you could think of that as it's heavier. It's thinner than continental crust, as you can see in the picture, and it's considered younger. Continental crust, on the other hand, is lighter colored, mostly granite. So if you've ever hiked, gone to the mountains, the rocks that you see, the mountains are typically made of granite. It's less dense, it's thicker, as you can see in the picture, and it seems to be older. And then on the last slide here, I just put a comparison of the two types of crust so you could see the difference in thickness, what materials make them up, and the thing I just want to point out is the thickness, because oceanic crust, as we'll see in 2.2, when it splits, magma can rise up between the cracks in oceanic crust because it's not very thick. But on continental crust, because it is much thicker, when it splits, it doesn't typically split all the way down, and magma is not able to rise up and fill in the crack. All right, that's all we have for today.